Hey guys, welcome back. I got my trash hat on today. Look how lovely that is. And today we're going to be working on volumes of solids of rotation. And again, this is one of those skills which is the really the summation of calculus B of AB, really, calculus AB. So if you remember what we did yesterday, we did volumes where the volume was just basically equal to the integral of an area formula. Now, if you keep that in mind, today is going to go by really smoothly because it is exactly the same concept. All we're going to be doing is integrating a bunch of area formulas. So really keep that in mind here. So for question, or I guess for context, we have this thing about the lathe and the pottery wheel. And most of the time most of us have probably seen one or more of these in action, and it's kind of like this rotational sculpting that gets done, in traditional crafts an awful lot. And that's the way that things are going to happen here. We're going to be rotating, and based on the rotation, we're going to create a shape. So that's how you want to think of things. Here is our problem. We want to rotate this region right over here. This is from our Han Solo on the last section. But 2 plus sine of pi x over 4, we want to rotate this around the x-axis. So to kind of envision what that looks like, we take this shape and we draw or we trace out the reflection across the x-axis. And then we draw discs that go from the top curve to the bottom curve. And you'll see that kind of looks like a vase. Or maybe like a bowling pin. I don't know. So we draw the reflection. We fill in the space with a bunch of discs. And that's what's going to give this method its name. This is called a disc method. And if you look at this, you can already see that we're just going to add together the volumes of all of these disks. And that's going to be our volume of the entire thing. So this is calculus. It's the same thing that we did with our Riemann sums. It's the same thing that we did with our slicing method. And this is just a fancy slicing method, really. So a typical cross-section perpendicular to the axis of rotation, and it's going to be a cylinder. You may not, I don't know if you see it as a cylinder. It's a very thin cylinder. Most of the time we would call that a disc. So a volume of a disc or a cylinder is the same as the volume of any prism. It's a cross-sectional area multiplied by the depth. The only difference is this time the cross-sectional area is pi r squared. We get our pi r squared right over here. And of course our depth is going to be our delta x. So when all gets said and done, the volume of one cross-section is going to be pi. This is my function squared multiplied by delta x. Again, we're going to put together all of these cross sections. So we're going to add them together with the sigma. And as we let delta x go to 0 and we add in all those areas, this sigma becomes an integral. So we're just going to integrate from 0 to 7 pi times the function squared. And I don't want to leave you hanging. So what is that volume? Well, I've gone and I've put y1 in my calculator here. So from the home screen, we're going to integrate from, I believe it was 0 to 7 pi y1 squared and then dx. That's pi r squared. Good, 104.646 cubic units in this case because it's a volume. There we go. I've just gone and I've copy and pasted that calculator screen onto the calculus trainer. So that's nice. Look at that. There's actually nothing new here. The only thing that's changed is in the area formula is now pi r squared. Okay, so as long as the cross sections are prisms or cylinders, we're going to compute area with the same thing. Volume is a limit as delta x approaches 0 of a sigma of area multiplied by delta x. And that limit becomes the integral from a to b of the area formula dx. And if we're talking about rotations in particular, we're saying that the area is equal to pi r squared, where r is going to be equal to the function minus the axis of rotation, or the axis of rotation minus the function, depending on which one is above which. AOR, of course, is axis of rotation. We'll be using that throughout, the course. So this is the same step-by-step for computing volumes with calculus. Find the coordinates of every corner on the base. Find the equation of, well, this is a little bit different. This is R instead of L, because the volume of a circle, or the area of a circle, is always dependent on the radius. For rotations, that radius is going to be f of x minus the axis, or the axis minus f of x. I feel like I just said that because I did. Once you have r, you find the cross-sectional area, and that's pi r squared, and then you just integrate. Let's look at this right here. Find the volume of the solid created by rotating the region bound by the coordinate axis and 4 minus 1/2 x about the x-axis. So, same 4 steps. First thing is find the coordinates of the corners, and we see all the corners here already. There's 0, 4, 0, 0, and 8, 0. Already looking at the x-coordinates, and you can see that the smallest value for the x-coordinate is 0, so you're going to say a is 0. The biggest value for the x-coordinate is 8, so you're going to say b is equal to 8. Now, instead of a length, we're going to use the radius. So the radius here is the distance from the axis of rotation, which is down here. Maybe we do that in red. The axis of rotation here to the curve up here. That's going to be the radius. And it's going to be the difference of the y-coordinate up here minus the y-coordinate down here. Now at the top, the y-coordinate is 4 minus 1/2 x. And at the bottom, the y-coordinate is always going to be equal to 0. Next, the area. Since we know the cross-sections are going to be cylinders because of the rotation, we know that the area is going to be equal to pi r squared, which is pi multiplied by 4 minus 1/2 x squared. And ladies and gentlemen, that's all we really need, because now we're going to integrate the area formula. So we're going to integrate from 0 to 8 of 4 minus 1/2 x squared. Now, before I did that, when I did this last time, I used a u substitution, and I think this time I'm not going to use the u substitution, just so you can get a variety of techniques here. So we're going to go from 0 to 8, and let's expand this binomial. So expanding that binomial, we get 16 minus 4x plus 1/4 x squared. And now we're ready to integrate. So we'll chuck that pi on the outside. The antiderivative of 16 is 16x. The antiderivative of 4x is 2x squared. And the antiderivative of 1/4 x squared is 1/12 x cubed from 0 to 8. And then now we just substitute things in. We've got pi multiplied by 16 times 8 minus 2 times 64 plus 1/12 times 5/12 minus pi multiplied by 16 times 0 minus 2 times 0 plus 1/12 of 0. Once we calculate all of this, we get 128 pi over 3, which is about 42 point, no, it's not. It's about 134.041 cubic units. Now, I almost made the classic mistake there. I forgot to multiply by pi. So just remember that it's really easy to forget about pi when you calculate the answer. It's probably safest if you don't bother with multiplying everything together and just leave it in terms of pi. There's nothing wrong with 128 pi over 3. Which leads us to our important ideas here. It's the same base formula for every volume that we're going to do. It's just the integral of an area formula. The only difference is because it's a rotation, the area formula is always going to be pi r squared. Every rotation is a pi r squared formula. Now, the radius could be either the function minus the axis or the axis minus the function. Really kind of depends. And finally, depending on the orientation, actually this is what we were talking about, depending on the orientation of the axis in f of x, the radius could either be the axis minus the function, and that's if the axis is above the function. You know what, I'm going to draw this. So first off, if the axis is above the function, then the radius is the axis of rotation minus the function. And then conversely, if the function is above the axis of rotation, then r is equal to f of x minus the axis of rotation. So this is a visual of when to use which. So for check your understanding, we're going to find the volume when the region bound by the curve y equals sine x and x equals 2 between 0 and pi is rotated about the line x equals 2. So let's kind of draw this. Now, we don't need to have a calculator here for sine x. We all know what sine x looks like. So let's first start by drawing a coordinate axis. And, I didn't mean that to be in red. So here's our coordinate axis, and we'll draw sine of x in red. No, this is blue. And we'll go up, and then we go down, and then we go around. Okay, so this is y equals sine x. And then we need the line x equals 2. So we'll just go ahead and grab a horizontal line. We'll do this in red because this is also happens to be the axis of rotation. Okay, and we're going to go between 0 and pi. So this is the region that we're talking about here, from here to about here. And we're going to go all the way down over here. We're going to find the volume. This region right here is going to be rotated about the red line. Okay, over here, this is x equals pi. Over here, x is equal to pi as well. From over here, x equals 0. And down over here, x is equal to 0 as well. Now, we're going to rotate this around this line right here. So this is our axis of rotation. Is y equals 2. This should be y equals 2. This should be y equals 2 as well. Don't worry, that'll get fixed in any further copies of this. And yeah, so let's first of all start with the corners. Did we get the corners? Yeah, we've got the x-coordinate of all the corners already, 0, 0, pi, and pi. So it looks like A is going to be 0 and B is going to be equal to pi. Cool. Next, the radius. Okay, the radius is going to be the distance from the axis of rotation to the curve. So this one right over here. Now, unlike the previous ones we did, the axis of rotation is on top and the curve is on the bottom. So the radius here is going to be the y-coordinate on top, which is 2, minus the y-coordinate on the bottom, which is sine x. Okay, so that's the corners, that's the radius. The area formula, well, the area formula is pi r squared, which is pi multiplied by the quantity of 2 minus sine x squared. And lastly, we're going to integrate. So the integral from a to b of ax dx, that's going to be the integral from 0 to pi. Area formula is pi, and this is what, 4 minus 4 sine x plus sine squared x dx. So I've already gone and I've expanded that just to make things a little bit, I don't know, little smoother. So we can integrate all of these first two terms pretty easily. But in order to integrate this last term, we don't have an integral for sine x. So we need to use what's called the power reducing formula. Freshly copied and pasted from the internet, here are the power reducing formulas. You will only really need to use the last two. Okay, so let's get to substituting that stuff here. We're going to go from 0 to pi. Pi, 4 minus 4 sine x, plus, and I like to put the 1/2 out in front, so 1/2 of 1 minus cosine 2x dx. Okay, maybe we'll simplify this a little bit more. So how about the integral from 0 to pi of pi multiplied by, well, this is going to be 4 plus 1/2, so 4 plus 1/2, we'll just keep that at 4.5, minus 4 sine x plus 1/2 of cosine 2x dx. All right, this looks pretty good for integration, so let's get that done. So pi, antiderivative of 4.5 is 4.5x. Antiderivative of 4 sine x is negative 4 cosine x. And then the antiderivative of cosine 2x is 1/2 of sine 2x. So 1/2 and 1/2 is 1/4 sine 2x. And that's going to go from 0 to pi. Substitute all of that stuff in, and we get 4.5 pi plus 4 times cosine of pi. Cosine of pi is negative 1, plus 1/4 of sine 2 pi. Sine of 2 pi is 0, minus pi, and this is going to be 4 times 0, plus 4 times the cosine of 0, and the cosine of 0 is 1, so be careful with that, plus 1/4 of the sine of 0, which is still 0. All of that is 4.5 pi squared minus 8 pi. Now, for all of these, if you are choosing to do these all analytically, these are going to be very important to you. So these are pretty much the last trig formulas that I would have you memorize. So that's it for us. It was a lot of fun. Hopefully you get this. Remember, it's just the integral of the area formula. And if you're rotating, it's the integral of pi r squared. As long as you can find the radius, you're going to be great. See you next time.